So, I've been asked several times to make a tutorial about how to use Crumble, which is a circuit editor I was kind of forced to write in order to finish a paper. So I was making this paper about doing Y-basis preparation in the circuit surface code, and I couldn't get the circuit right. I basically knew what it had to be, but all the details kept being wrong, or I would fix one thing and break another thing, and just found myself going in circles. And part of the problem was I didn't have any way of easily looking at the circuit and asking questions about it and quickly getting answers. So this circuit that I was actually trying to make is one of the example circuits here. It's the Y-basis preparation example. Um, it's a somewhat complicated circuit. I'm not going to be going over this circuit in this video, um, but it was the motivation for making this tool originally. Okay, let's just clear that out and go back to my empty screen. So the main thing that Crumble does, the reason that you would use it instead of pen and paper, is that it can track Pali errors around. So let's make a very simple circuit. So I'll select this qubit here. These squares, by the way, are the qubits. I select this qubit, I hit H to insert a Hadamard gate. Incidentally, there's this little keyboard viewer thing up here that you can use to see what I'm hitting, because almost everything in Crumble is keyboard shortcuts. Actually, I don't want this H in the first layer, so I'm going to hit delete to remove it. I'm going to hit E. E here is the shortcut for next layer. I hit E to go to the next layer and put it there. And then hit Q to go back to the previous layer. And then I'm going to hit X and 1. So what that says, roughly speaking, is I would like to insert an X error into tracker number 1 or flow number 1. And I would like you to tell me what this error does as it goes through the circuit. So here on the timeline view on the right side, you can see that this X error is inserted on this qubit. Then the Hadamard gate transforms it into Z basis. Or I guess I have to explain the color convention in order for you to understand that. So Crumble uses the color convention RGB equals XYZ. That means red is X, green is Y, blue is Z. So this red triangle means I put in an X error. This red line means there's an X error propagating into the Hadamard. And then this blue line exiting means it became a Z-type error as it exited. That is in fact what Hadamard gates do. They turn X-type into Z-type and Z-type into X-type. If I step forward in the circuit by hitting E, you can see that it changes from red to blue in the layer viewer as well. I can then put some more operations in, so I can select this qubit, hold Control to select another one, then hit C to put in a CNOT gate, go forward another layer, put in an S gate. Now, basically the error is currently not interacting with these things. Z-type error commutes with the control of a CNOT, so it just passes right through. It doesn't end up talking to the S gate either. But if I go back here and I switch this from X-type to Z-type by hitting Z1, now the Hadamard turns the Z-type error into an X-type error. The X-type error doesn't commute with the CNOT, so it goes on to the other side as well. And then the S gate turns that X-type error down there into a Y-type error. So Crumble makes it very easy to ask questions about how errors propagate around. This is a very simple circuit, but it can also do it for complicated circuits. A crucial thing to understand is it's also showing how knowledge moves around. Instead of saying that this is an error that I'm inserting, I could instead say, this is something I know. At this time, somehow, I know the Z operator of this qubit. And I would like to know how these gates have transformed that knowledge into something different. In particular, it has transformed it into the X times Y operator. Now, typically, you won't just have sort of like free floating knowledge like this. It'll come from somewhere. And in particular, it'll probably come from something like a reset gate. So what a reset gate does is put a qubit into a known eigenstate of the Z operator. So the reason I know Z here is because I reset the qubit into something where I knew it. And what this diagram is now telling me is that at this point, that reset means that this compound operator is deterministic, assuming no errors. And instead of having these just kind of continue forwards, I could actually terminate them. I could measure this qubit in the x basis by hitting M and X for an x basis measurement, measure this qubit in the y basis for my, and I could hit 1 on each of these, and now I have a completely enclosed shape. And a closed shape like this is basically saying, I know the parity of these two measurements because they come from this reset. These are the kinds of things you're constantly looking for in error correction circuits. Things that you know because of something else in the circuit. And Crumble makes it easy to see how these things propagate around. Okay, so that's the simple example. Now, what I want to do is show an end-to-end example of doing a full error correction circuit. In particular, we're going to do the standard surface code cycle memory experiment. So we're going to make this example circuit, okay? End-to-end, all of it. So let's do that. So what I like to do when I'm starting a circuit is I like to set up a reference, a visual reference. I like to draw little shapes that can guide my eye in later layers. So I'm going to select the corners of a square by holding Control and clicking. And then I'm going to hit P for polygon and then Z for blue. So the XYZ equals RGB thing is being used here to set the color of the polygon. And then I want a red polygon, so PX. Another red square, PX. Incidentally, instead of clicking them one by one, I can box select like this. I don't want this middle one here. So what I can do is I can click and I can hold Alt, which in Crumble means basically subgrid focus. So it'll only get one of the subgrids instead of both. I hit P sub Z for a blue thing. And now that I have this sort of basic tiling pattern, I can copy with Control C and go over here and paste with Control V and make a big pattern relatively quickly. Then if you're familiar with surface codes, you know I need these two body operators on the side, which I'm just going to go through and do. Unfortunately, these are less repetitive, and so you can't really copy paste very much. So you just have to do them each individually. But now we've drawn a picture of a surface code, and we're going to start filling in operations. So I'm going to go forward one layer before I put in operations, because if I put operations into this layer and then I start copying them around, I'll accidentally copy the drawing as well, and I don't want to do that. I just want the operations. So what happens in a surface code circuit? Well, it's going to measure each of the stabilizers by resetting a measure qubit, and then interacting that measure qubit with each of the data qubits around it, and then measuring that measure qubit. And basically the stuff that we have to get right is, in what order do we touch these data qubits, and what way around is the CNOT gate. Now to do things a bit more efficiently, what I'm going to do is I'm going to select all of the Z basis measurement qubits ahead of time. Oh, actually, I can see that this is the wrong color. Let's fix that and go back. Okay. Or, oh, geez. Just got to do a bit of a more complicated fix here. There we go. Anyways, yeah, so I select all of the Z basis operators. Now, when I hit R for reset, I'm going to put an R on every one of these in parallel. And when I go to the next layer and I want to put in a CNOT gate, the leftmost, topmost qubit is going to be the reference here. And if I ask for a 2-qubit gate while hovering over some other target, I'm going to get it for all of them at once. So last time when I made a 2-qubit gate, I selected 2 qubits and then hit C to get a CNOT gate. Here I'm selecting the qubits, many qubits, and then I'm hovering over the target for the reference qubit, and then I hit C and it puts in a CNOT for every one of them, kind of following what the reference is doing. So this can save a lot of time doing it this way instead of one gate at a time. I happen to know that the standard surface code cycle, you always want to move the order in which you access the data qubits. You want to make like a Z pattern or an N pattern, something like that. So I went up and to the left. So then I'm going to go, let's say, up and to the right arbitrarily. And then we're going to go diagonally across. And then we're going to go down and to the right. Now for Z-basis stabilizers, these CNOTs are actually the wrong way around. We want the control to touch the data qubit and the target to touch the measure qubit. We can fix that by hitting F. So that's short for flip. And all of the CNOT gates that touch your selection will invert their targeting control when you do this. So I'm going to go through each of the layers doing that. And then I'm going to measure. Incidentally, I'm going to get rid of these kind of crufty ones on the side later. Now we're going to do the same thing in this X basis. I'm going to do a bit of a trick in order to quickly select all of these X basis things in the middle. I'm going to select, box select like this, hold Control for invert selection, hold Alt to get the subgrid, and then let go. Now I've got the red ones in the middle. I'm going to unselect these side ones, select those side ones. I now have all of the X basis measure qubits. I'm going to hit R and X together to get an X basis reset. Incidentally, there's basically a little language for the gates in the keyboard shortcuts. Like there's certain adjectives, basically. So the way I ask for an X basis variant of a reset is I combine X and R, which are short for X basis, and reset. A more complicated example of this is, suppose I want the Y basis parity measurement. That would be Y for Y basis, M for measurement, and a C for 2 qubit. There's also things like CW to get a CX swap, because W is swap in the adjective language here. Anyways, we don't want any of those. We just want kind of the standard gates for this circuit, so we're going to move on. In the first layer, we should go in the same direction in both bases. So I'm going to put that 2 qubit gate in. I can see that the Z basis ones are going up and to the left, so I also go up and to the left in the X basis. Then for the second layer, I want to do the opposite. So Z basis going up and to the right. I want to go down and to the left, like so, and across the diagonal, and then bottom right. And then measure in the X basis. And now we can go around cleaning up this cruft around the sides, which I'm just going to do by smashing delete across the layers. Now, this should be a correct surface code cycle, assuming I haven't made some stupid mistake. If some mistake comes up, I'll just let that happen organically if it does and fix it. Then we'll deal with that when it comes up. For now, I would like to start annotating detectors in this circuit, but to do that I actually need 2 copies of this round. Now I could go to each layer, select nothing, copy to get a copy of the whole layer, move forward, paste, go back, copy, go forward, paste. This is somewhat tedious. Instead what I'm going to do is go to this import-export button, which gives me a stim circuit corresponding to the current contents of the editor. And it's in text. And text is very easy to copy paste. And so I'm going to do that. This is maybe a little bit jank to do it this way, but text is incredibly flexible. And so you just end up sometimes going into the text and doing something weird like this because it's more convenient. So now I have 2 rounds. How do I check if they're correct? Well, what a round is supposed to do is it's supposed to prepare every stabilizer of the surface code, and it's supposed to measure every stabilizer of the surface code. So I'm going to be using the first round to sort of check that I'm preparing things, and the second round to check that I'm measuring things. And specifically, I'm going to measure the things prepared by the first round, and then the combination of those 2 things is going to form a detector. So let's look at this one, for example. I include this reset, and I follow it forwards. And I see it has become this 4-body operator I'm trying to make, plus this measurement. If I go forward another step, let me put an empty layer in so this is more clear what's happening. I have this 5-body operator. I've told Crumble I really care about this 5-body operator, and it's telling me with this magenta square, this reset has just destroyed that 5-body operator you cared about so much. The way I fix this is I say include the measurement. I'm basically saying I don't care about the qubit after this layer. I care about the bit that came out of the measurement. So if you forget to include a measurement, you'll tend to see those magenta rectangles indicating that you've made a mistake somewhere. So this reset propagates into this 4-body operator times the classical bit produced by this measurement. That is preparing one of the stabilizers of the surface code. Then we want to measure this stabilizer. Currently, if we just step forward, it will just stay where it is. Okay, it'll get kind of pushed around a little bit by the gates in between, but it stays as 4-body operator at the end. We instead want it to collapse onto the measurement. This is a very common problem to run into when you're designing an error correction circuit, and especially when you're doing it in Crumble, is you have to combine facts to get the collapse. We know this 4-body operator. We separately know this reset produces some 1-body operator, but what we need is the combination of them. So I include the reset with the 4-body operator, and then it will collapse down. In the surface code, this is super straightforward. You just always include the reset or the measurement that's in the middle of the stabilizer. But in more complex codes, this can get very non-trivial. So let me actually show an example of this. So if I go over to the color code example, which uses the super dense cycle, clear all pally marks, and I try to find, like, how do I get the stabilizers? Okay, I followed this reset forward and it turned into a stabilizer. Now I want to collapse it. If I just include this reset in the middle, what happens? It doesn't collapse. It gets bigger. What if I don't include anything? Then what happens? Then it moves down. What if I include this reset and this reset? Then it just stays where it is. And what if I include the reset below it? Then it collapses down. Okay, this is a very common issue to run into when you're making a more complicated stabilizer circuit. Is, how do the resets relate to the measurements? Okay, I'm just going to hit undo until I get back to my circuit. There we go. Okay, now I want to show you the structure of this detector, but it's currently going off the bottom of the screen. So what I'm going to do is I'm going to select the qubits that I know are relevant. I'm going to hit Set Timeline Focus, which is only going to draw qubits in the timeline view that have been included in this selection. And now we can see that this prepare a stabilizer and then measure it forms this closed object. This object is what we call a detector. Or sometimes when we say detector, referring to just the measurements that we're comparing, so these two measurements that are involved in the object. This gives you a little bit of fault tolerance because from this closed object, you can compute how these two measurements are supposed to relate to each other. In this case, they're supposed to agree. And if an error happens on any place where these blue lines are going, so for example, if I put a Y error right here, that will flip the relationship between the two measurements. Their parity will go from even to odd. And we know what the parity is supposed to be, and we see it's the opposite. So we know that there has to have been an error somewhere on this blue shape. And then the whole game of a fault-tolerant circuit is to make an interlocking pattern of these blue shapes and red shapes, or maybe multicolored shapes, such that errors get caught. That when an error flips certain detectors, you can figure out the location of the error up to certain details that, like, you don't have to know the exact location. You just have to know something that's good enough to get the correction right. Now, in order to put this detector into the circuit, so currently if I look at the circuit, we see that it's just kind of these like pragma mark commands, which are actually just comments. I want it to be an actual detector declaration. What I do is I hit D, 1. So D for detector, 1, because I've only been working with flow number 1 this whole time. Now if I look at the exported circuit, there's a detector declaration referring to those two measurements using STIM's syntax for that. To make this circuit complete, we have to include every detector. And we have quite a few of them actually. And I'm going to go through every single one of them. I'm not going to explain every single one of them. I'm just going to do every single one of them. So every one of these resets is going to be preparing a detector. So I'm going to go to each of them and going to hit a separate number. So for this one, I'm going to hit number 5. If I instead had hit number 1, I'd be doing like a combination of these two resets in one of the flows, but I want separate flows because I'm going to make separate detectors, so I hit different numbers. Let's go up to 7. Let's step forward towards the measurement layer. I know all these measurements have to be included, so I'm going to include them. 1, 2, 3. Actually, there is a shortcut for this. There's a shortcut that says if a measurement is touching a flow, include the measurements in the flow, and that shortcut is K, and then the number that you want to apply this to. So K4, it completed that one. K5 will complete this next one. K6, K7. Alas, there is not a similar shortcut for the resets, but we can do it for the measurements. Okay, so I've now made 7 separate flows that form these kind of closed objects in space-time. Let's take a closer look at those by setting the timeline focus. You can see it's a bit of a mess, but we can turn them all into detectors by hitting D, 1, 2, 3, 4, 5, 6, 7. Now the mess is much less. You can see there's still little dots. These dots indicate, there's a detector passing through here. You can see them in the timeline view. You can also see them in the time slice view. Let's clear the timeline focus and let's keep adding more detectors. Let's do these 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think I lost count there. Whatever, it doesn't matter. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Do these manually again. Then include these automatically. And then turn them into detectors with D. Just a few more to do now. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And detectors 1, 2, 3, 4, 5, 6, 7. Now, again, unless I've made some silly mistake, we now have annotated all the detectors between these two rounds. A way to check on that is we go to this layer in between the measure and the reset, or here I've put a layer in so that there is one, and we can see that in the bulk, in the middle, not touching the sides, there's 2 blue dots and 2 red dots on every qubit. For the surface code, this is a good check. For arbitrary codes, this may not be the case, but for the surface code, that's the pattern of dots you want to see. And then on the sides, one of the dots will be missing, depending on which side you're at, and in the corners, 2 dots will be missing. It's just a simple sanity check you can do. I would also like to be able to do the sanity check halfway through the round. Currently, there's not 2 dots of each color, but that's only because I only have 2 rounds. I'm going to copy paste the second round, including its detector annotations. And just because of how these detector annotations behave, because they kind of refer to measurements by relative index, this is just going to magically make the detectors for the second to third round also exist. Okay, so now I have 3 rounds. This is the first round. This is the second round. This is the first round. And if I go to the very middle of the second round, insert an empty layer to see, now there are 2 blue dots of each color, except when you get close to the sides. Interestingly, here the dots are grouped by color, and here they're not. Don't know why that is. Doesn't really matter. Okay, so we now have 3 rounds. We've annotated the detectors between the rounds. What we need is to put the ends on the circuit. We need to put a fault-tolerant initialization. So in the surface code, fault-tolerant initialization can be done transversely. To prepare a logical 0, I can simply prepare every data qubit into the 0 state with reset gates like this. This creates new detectors. So for example, these 4 resets make a 4-body operator. And then if I also include this reset to make it collapse, it goes to this one measurement, and I get this. I'm going to set the timeline focus. I get this closed space-time object again. So that's a valid detector. So I just have to do every one of those. So that's one of them, 2, 3, 4, 5, 6, 7, 8, 9, 0. Incidentally, if you look at your keyboard in sort of a standard American keyboard, like English, you'll notice there's a dash to the right of 0. Yeah, dash works. So does equals. Anyways, we step forward a thing, then we have to include all of these, which we include in basically the same way, just include the same number for the same stabilizer. Step forward, and now we can do the auto thing, and then the auto detector thing. And so now we have a fault-tolerant initialization declared as well. If we go to the middle of the round, we can see that now there's 2 blue dots inside of the bulk. There's not 2 red dots, but that's pretty typical when you're right next to an initialization layer. The X-basis stabilizers haven't established themselves yet. We're now going to do the same thing on the other side of the circuit, but with measurements instead of reset. So transversal measurement in the Z-basis. And again, we're going to get just Z-basis detectors from this round to the end. So for example, if I annotate this reset and I follow it forwards, it goes into this measurement and also these measurements. This is actually much easier to annotate than the other case because I only have to arduously select these resets once, and everything else is measurements that can be auto-completed. Ooh. Ooh. Oh, I hit L by accident. 9, yes, please include all those measurements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 dash equals. And then turn that all into detectors, please. So now we have an end-to-end fault-tolerant circuit with all of the detectors annotated, unless I've made some mistake. The only thing left to do is to annotate the logical operator. Now, I can never remember if the logical operator goes this way or this way. I know it's going to be some column or some row, but is it a column or is it a row? This is an example where Crumble helps a lot. I just say, maybe it's a column. Include that. Oh, that breaks. It's not a column. Maybe it's a row. That works. There's no magenta, so it's the row. And then I go to the end of the circuit by hitting end, and then I can include the measurements. This is the logical operator, annotated here. It's in flow number 1. I can move it to an observable in the actual circuit by hitting O1. And if I go and look at the end of the circuit, I see an observable include instruction. So we should have a correct circuit now. Let's really check it. So I'm going to take the circuit, I'm going to copy it, and I'm going to go over to a Python environment. And I'm going to check it with stim. So I'm going to install stim, import stim, and say circuit equals stim.circuit, string, and I'm just going to paste in what I got. And then I'm going to make a diagram of the circuit. Let's make it a timeline diagram, a picture SVG. Actually, I probably want time slice, not timeline, because it's like a 2D circuit. Yeah. And actually, I'd really like to see the detector structure. So I'm going to say det slice with ops. And then I can kind of look at these pictures and see if I see like any shapes missing. Like maybe this shape here wouldn't be there, and I could notice that. It looks okay. It's pretty easy for something to sneak by still here. Oh, incidentally, if you're wondering, like, how do you know this random string? It's in the doc string. So if I print out the doc string for this method, it includes all of these different options for what the graph could be. Also, in Colab and in other Jupyter Notebook environments, you can say method question mark, and it'll give you this thing on the right that shows you the documentation. Anyways, so this picture looks fine to me at first glance, but I'd really like to have the computer check it over. And the way to do that is to compute the graph-like distance. So a surface code is supposed to be matchable, so the graph-like error is an appropriate thing to compute. And this is supposed to be a distance 5 surface code. Go back to Crumble. You count the data cubes from one side to the other. 1, 2, 3, 4, 5. Should be distance 5. So I want to see 5 here. I don't have any noise declared in the circuit. I have to write code to put noise into the circuit. Just a moment. Noisy circuit equals to circuit. Go over the instructions in the circuit. If the instruction is a CNOT gate, then the noisy circuit should get the instruction, but also an instruction to polarize the qubits that were touched by the gates with some arbitrary noise parameter. It doesn't really matter for computing the distance. If it's an MX or M or MX, then I want to append the instruction. I don't want the extra depolarization. I just need the measurement, but I have to make it a noisy measurement like that. And then if it's a reset or an X basis reset, then I want to append it, then depolarize, not don't depolarize before, because that would remove it. It would remove the noise to reset it away. And then if I forgot something, please warn me. String indices must be integers, not tuple. Made some silly mistake. Oh, I didn't put the keyword in. Forgot qubit coords. Oh, right. All the annotation instructions. Those just have to go through on modified. So if the instruction is qubit coords or detector or tick or observable includes, then just append it. Okay. I should probably look at the circuit just to make sure that there's no gotchas. That looks right to me. Sort of looks like the same thing, but with a bunch of red boxes, meaning that there's errors about. Okay, now let's look at the graph-like distance of the noisy circuit. 3. This is supposed to be 5. We have made a mistake. Typically, in a surface code, when you see that your distance is nearly half of what it's supposed to be, you've got your gate ordering wrong. Yeah, this is almost definitely hook errors. So let's look at what happens if I put an X error on the measurement qubit halfway through a round. So put it on the measurement qubit, step forward, and we see that it spreads it out vertically. The Z operator is running horizontally. So spreading out vertically cuts the number of these things that you need in half. The fix for this is to reorder these rounds. So I'm going to take this one, I'm going to cut it, go to before that one, and paste. And now, if I put an X operator in here, it should spread horizontally instead of vertically. Yeah, I can see it spreading horizontally. That's what it's supposed to be doing. I have to make the same change to the other two. Another way to do this is to isolate them, go to the first, so that there's empty layers before and after, and then go to the first one and hit G. What does G stand for there? I don't know. one more than F. Okay, so I've flipped the order. Copy. Go up here. Paste over the old circuit. Step through. Distance 5. Okay, so we've succeeded. We have made an end-to-end surface code circuit in Crumble. And we debugged a problem that we created. We realized that there were hook errors. We checked that there were hook errors. We fixed it, and then we checked the fix. That's kind of the main deal here. There's a lot of kind of technique in using Crumble. Like there's problems that will come up that you come up with ways of solving them that just take fewer keystrokes. I could probably be here all day just talking about stuff like that. I don't really have a list in my head of it though. I just do them when they come up. That I don't know how to make a tutorial for that other than to just show you me doing this. That's actually part of the reason I structured it this way of me doing a circuit, because I know there's a bunch of things that I did that otherwise you just never would have heard about. I mean, there is this read the manual link. You can click on this. You can read through all of the different keyboard shortcuts and come up with things. But, software engineers know no one reads the manual. And you really should read the manual because it would be very helpful, but I know you won't. But you should, but you won't. Other than that, I guess there's not much to talk about. I think I'm going to end the tutorial here and just leave you to discover how to use this tool better, or even better than that would be if someone made a better tool than this. Okay, this tool has many suboptimalities that could be fixed. It could be improved upon. If you want to do something cool in quantum error correction, making a better Crumble, I think, is a completely viable project if you have a little bit of coding skill. This tool, if you put in big circuits, it's slow. You saw me doing repetitive motions that probably there could be something to help with that. There's a million things that can be done to make this tool better. And I really hope that someone does that. And I think I'll close on that note. So good luck with all your circuit editing.